Hello lovelies, in this video we're going to be going through everything that you need for your AQA GCSE Chemistry Paper 2. And this is in a grade 9 standard, so we're going to go through point by point, explaining everything that you need. Now, anything that's separate slides can be marks, or you can use the timestamps in the description down below. Also in the description you'll find a link to our masterclass, our boot camps and our projected papers for this year, where Charlotte, who's made these videos, thinks about what's going to come up, and then the video walkthroughs of the predicted papers where she shows you how to answer the questions so that you can probably show off to the examiners exactly what you know.
The rate of reaction tells us how quickly reactants are used up or products are made. Now we can calculate the rate of that reaction using one of two equations. We can say that the mean rate of reaction is equal to the quantity of reactant used divided by the time taken. Or alternatively, if instead of measuring the amount of reactant that's used, if instead we're using the quantity of product made, we can say that the mean rate of reaction equals the quantity of product made divided by time taken. Now, the quantity of the reactant or product made can be measured in a few different ways. It can be measured in terms of grams if we're measuring a mass. It can be measured in terms of centimetre cubed if we're measuring a volume. Or we can even measure it as moles. Now, dependent on how we measure the quantity of reactant or product, will determine what the rate of reaction is measured as. So the rate of reaction could either be measured in grams per second, in centimetres cubed per second, or as moles per second. However, I do want to say that check what your answer line wants, because sometimes you'll even see it as grams per minute or centimetres cubed per minute, or maybe even something different. So we have to be aware of what the question wants and make sure that we use the correct units for the question. However, if they don't specify something unusual, it will be grams per second, centimetres cubed per second, or moles per second. Graphs can tell us a lot about the rate of a reaction. So if we look at a curve of amount of substance against time, if the curve is steep, then that tells us that we have a high rate of reaction, which means that the reaction is happening quickly. However, if our curve is comparatively more shallow, then this tells us that we have a low rate of reaction, and this tells us that our reaction is happening slowly. If we want to experimentally determine the rate of reaction, we have two different methods. Firstly, if we're using the mass, we can measure the change in mass of our reaction mixture. To do this, we would use a balance and we would use a stopwatch. The stopwatch is very important because that measures the time taken. Now we'll use this method if a gas gets produced, as the mass of our reaction mixture will eventually decrease with time. However, if we want to measure the volume of gas produced instead, then we would use this setup here. And we could either use our reaction mixture connected to a syringe, or we could connect it to an upturned measuring cylinder. We would also always need to have a stopwatch. Whenever we're working out the rate of anything in science, we need a stopwatch to measure our time. Now this method is perfect if a gas is produced as well. This time though, we're going to measure the volume of gas produced. Let's have a look at these experiments in a little bit more detail. Let's have a look at the method of measuring the change in mass. So firstly, you put your reaction mixture on a balance. You can see here that we have some cotton wool on the top of our conical flask. The reason why we use this cotton wool at the top is it will allow gases to escape, however it won't allow any other substances to escape. So what we're going to see is as this reaction takes place, if a gas is produced, the mass will decrease. We're going to measure the mass of the mixture on the balance and record it at regular time intervals. The rate of the reaction can then be determined using rate equals change in mass, which we measure using our balance, divided by the change in time, which we measure using our stopwatch. Now this particular method, because we're using a balance to measure a mass, the rate would have the units of grams per second. Now let's have a look at the method that looks at the volume of gas produced. So in this case, our reaction mixture is connected either to a gas syringe or to an upside down measuring cylinder. As the reaction takes place, if a gas gets produced, the apparatus of our measuring cylinder or our gas syringe is going to collect the gas. We can record the volume of the gas at regular time intervals using our stopwatch to determine those. And then finally, we can calculate the rate of reaction using the equation that rate equals the volume of the gas produced divided by the change in time. And the units in this case will be centimetres cubed per second because of course we're measuring a volume in this case. We're expected to be able to calculate the rate of reaction using graphs. So to work out the mean rate of a reaction between 2 points in time on a graph, firstly, we're going to use the graph to find the amount of substance at each time. Next, we're going to find the change in the amount. Then we're going to find the change in the time. And finally, we can now calculate the mean rate of the reaction. It's going to be equal to the change in the amount divided by the change in time. So let's put this into practice then. Let's work out the mean rate between 0 seconds and 30 seconds for this particular graph here. First thing that we would need to do is to have a look at the point at 0 and then have a look at 30 seconds. So that's just here. So now that we've done this, let's have a look at what the volume of gas is at each of those points, and of course what the time is too. We can use this to work out the change in the amount. So the change in the amount is going to be 60 minus 0, and the change in time is 30 minus 0. Now that we know this, we can work out what the mean rate of reaction is. We can say that the mean rate is going to be equal to 60 divided by 30, and that simplifies down to give us 2 centimetres cubed per second. Make sure that you're always careful of the units by looking at what the axes on the graph are in. We might also be asked to use the tangent to work out the rate of reaction at a specific point on a graph. Now to do this, if we want it at a specific time, say 30 seconds, you would need to start off by drawing a tangent to the curve at that specific time required. We would then need to find the gradient of the tangent, and the gradient would of course be that mean rate. So the mean rate is the change in amount over the change in time. It's important that you remember that the tangent is just a straight line that just touches the curve at the point you're being asked to find. And of course we also need to remember how to calculate the gradient. So once you draw that tangent, you're going to draw a little triangle, as big a triangle as you can, and the gradient will be the change in the y divided by the change in the x. But let's put this into practice, okay? Let's have a go at working out the rate of reaction at 30 seconds. So in order to do this, first off, we're going to need to take that tangent. See, I've used a ruler and use a pencil as well in the exam to just touch the curve at 30 seconds. Now that I've done this, I'm going to draw a little triangle out of this. And although it's good to just find a nice easy triangle, you need to also make sure that it's big. The bigger, the more accurate your answer. So here I can see that my triangle at the bottom, it hits at a volume of gas of 20 centimetres cubed, and at a point that I've chosen at the top of it, it's 88 centimetres cubed. This means the change in the amount, or that change in y, is 88 minus 20. Now if we look at the base of that triangle that we've made, the change in time, or the change in x, is 50 minus 0. So now we can go straight in and put this into our calculator. So we can say that the rate at 30 seconds is equal to 68 divided by 50. And that ends up giving us, if we put that into the calculator, 1.38 centimetres cubed per second. Again, make sure that you get your units right by looking at the axes of the graph. And there we have it, that's how we do it. Different factors can affect the rate of a reaction, and there are 5 main factors that we need to be able to talk about for this exam. Firstly, we need to know about temperature, then pressure, concentration, surface area, and catalysts. Before we look at all those individual factors, let's have a think about collision theory, because we're going to need to describe how those factors affect the rate of reaction in terms of something called collision theory. Now, collision theory is what we use to explain how different factors affect the rate of a reaction. Collision theory states that chemical reactions can only occur when reactant particles collide with each other with sufficient energy. So there's 2 key facts there. For a reaction to take place, we need a collision, and that collision needs to have sufficient energy. Now, when we say sufficient energy, we mean that it has at least the minimum amount of energy needed for a reaction to take place. And the name for this amount of energy is the activation energy. So let's get started with looking at how temperature affects the rate. And we're going to explain this in terms of collision theory. Well, if we increase the temperature, those particles will have more energy, and therefore they're going to move more quickly. As a result of them moving more quickly, we're going to have more frequent collisions. And because they're going to have more energy, there's going to be a higher proportion of successful collisions. Now, those are collisions which exceed the activation energy. Therefore, because we have more frequent collisions, and those collisions also have more energy, the rate of the reaction will increase. If we look at this graph here of amount of substance against time, we can see that when we have a higher temperature, the rate is faster. We can see that because it's steeper. And we make the maximum amount of products quicker than we do at a lower temperature. And the graph shows this because it flattens out earlier for a higher temperature than it does for a lower temperature. Now let's have a look at pressure. If we increase the pressure of a system, the particles will become more crowded. The result of this, if they're more crowded, a bit like you're on a busier street compared to a less busy street, is there are more frequent collisions. You're banging into everyone more. And therefore, the rate of reaction will increase. Again, if we look at the graph of amount of substance against time, we can see the exact same pattern. At higher pressures, we've got this steeper curve than the lower pressures, and it also reaches that maximum amount of substance faster than at lower pressures. And we can see that because it plateaus at an earlier time than at the lower pressure. Now let's look at concentration. Concentration and pressure are very similar, except concentration is referring to solutions, whereas pressure is really referring to gases. Well, as you can see in these diagrams, if you increase the concentration, the particles are more crowded, and therefore there are more frequent collisions, and the rate of reaction will again increase. Now this again you can see on our graph of amount of substance against time, the exact same pattern again. For higher concentrations, you can see that we have a steeper curve, therefore we've got a faster rate of reaction, and it plateaus at an earlier time than for lower concentrations. And this means that we've made our maximum amount of substance earlier than we do at lower concentrations. Now let's look at surface area. Increasing the surface area would mean taking something which maybe is a lump and grinding it down into a small powder. A good analogy here for our everyday life would be if you had like a sugar cube versus some powdered sugar. If we put the sugar cube in a drink, it's going to dissolve much more slowly than our powdered sugar, and the reason for that is that we have a bigger surface area when it's a powder versus a lump. Now the reason for this is if we increase the surface area, like we have when we have this powder, we increase the number of reactant particles exposed. Now as a result of that, because there's more exposed, there's going to be more frequent collisions again, and therefore the rate of reaction will increase. Again here you can see with this graph, when we have this greater surface area, which actually means smaller particles, we have this steeper curve whereas the smaller surface area, which would be our lumps, has a shallower curve. Now, I also want to mention here, and this is our little top tip, instead of seeing it referred to as surface area, we might see it referred to as the surface area to volume ratio. Now, bigger particles, such as our lumps, are going to have a smaller surface area to volume ratio than small particles such as powders. So make sure you're comfortable with either language. Now, the final factor that affects the rate is a catalyst. And whereas all these other factors were very similar in how we talked about them, catalysts are going to be a little different. So catalysts are substances that can speed up the rate of a reaction without actually getting used up. They provide an alternative reaction pathway with a lower activation energy. Remember, we said that the activation energy was the minimum amount of energy needed for the reaction to take place. So if we lower this activation energy, more particles will have this energy. So this means that we're going to have more successful collisions, and therefore the rate of reaction will increase when a catalyst is present. Now, this graph here we need to be able to recognise, and we need to be able to sketch really. Here we've got energy against progress of reaction. And you can see here this particular reaction is an exothermic reaction. However, you could see this for exo or endothermic reactions. The activation energy is the bump that goes up from the reactants, reaching a peak before it goes down to the products. And that activation energy is the difference between the reactants and that peak. You can see here that the activation energy with the catalyst is lower than the activation energy without a catalyst. Just like we said, we know that catalysts provide an alternative reaction pathway with a lower activation energy. So make sure that you can draw this graph or label one that they give you. Reversible reactions are shown using this symbol here. A reversible reaction is one in which the products can react to form the original reactants. So the reactants can make the products, but then the products can go back and make the reactants again. Now, an important thing about a reversible reaction is that we can actually change the direction of some reversible reactions by changing the conditions. One example of this is the thermal decomposition of ammonium chloride. Ammonium chloride will make ammonia and hydrogen chloride. However, this is a reversible reaction. Now, the special thing about this is when we heat the ammonium chloride, it will break down to ammonia and hydrogen chloride. However, if we were to cool that reaction mixture, the ammonia and the hydrogen chloride would react back together to form ammonium chloride again. So that shows here that the conditions can affect the direction of this reaction. Now, taking this a step further, if a reversible reaction is endothermic in one direction, it will be exothermic in the opposite direction. And importantly, equal amounts of energy will be transferred in each direction. So if it took in a certain amount of energy in one direction, when it goes in the other direction, it will give out that exact same amount. Now, there's a specific example we need to know here. We need to know that hydrated copper sulfate breaks down to anhydrous copper sulfate and water. Now, that process in that direction is an endothermic reaction. So it's going to take in heat energy. Whereas if we go the other way, the anhydrous copper sulfate and water can become hydrated copper sulfate, and that is an example of an exothermic reaction. Now that means that when we heat the hydrated copper sulfate, we will remove water, and that blue hydrated copper sulfate will end up becoming the anhydrous copper sulfate and water, where the anhydrous copper sulfate is white in colour. So we will actually observe a colour change here. Likewise though, if we cool down the conditions here, then we would see that the anhydrous copper sulfate and the water would go in the exothermic direction and make hydrated copper sulfate. So we would see the colour change from white to blue. So the next thing we need to know about is what is meant by equilibrium. we need to know that we have equilibrium when in a reversible reaction, forward and the backward reactions are both happening at the same rate. Now, this is assuming, of course, that there's no escape of reactants or products. So this is only assuming that we have a closed system. Yeah, so make sure that you learn that we have equilibrium when our reversible reaction has forward and backward reactions happening at the same rate. So reversible reactions can reach an equilibrium. Now, the position of this equilibrium can be controlled by three different factors: a change in the concentration, a change in the temperature, and a change in pressure. One thing that doesn't change the position of equilibrium, however, is adding a catalyst. This has no effect. It simply speeds up the rate of reaction. Now, this whole process of changing the position of equilibrium can be very useful for industrial processes where we're trying to make a certain product. The reason for this is if we can shift the equilibrium in the position of that product that we desire, we're going to be able to make our process more profitable. Now, we need to consider how each of these factors will affect the position of equilibrium. And to do this, we're going to consider something called Le Chatelier's principle. So Le Chatelier's principle states that if a system at equilibrium is subjected to change, the system will adjust to counteract that change. Let's have a look to start with the effect that changing the concentration has on an equilibrium. Well, first thing we need to know is when we increase the concentration of a substance, there's just more of it. And the whole point of this equilibrium is it wants to get things back to how it was. So if we add more of a substance, the equilibrium wants to get rid of it. So it's going to shift to the other side. So if we increase the concentration of a substance, the equilibrium will shift to the opposite side of that substance to get rid of it. Now, if we decrease the concentration of a substance, the equilibrium will actually shift to the side of that substance. The reason being is if there's less of it, we need to make more. So if we look at this particular reaction, this Haber process, and we ask ourselves, what will happen if we increase the concentration of nitrogen? Well, if there's more nitrogen, the equilibrium wants to get rid of it. So it is going to shift towards the right, and it's going to make more ammonia. So that's how we always want to think about them when we're looking at changing concentration. Now let's have a look at the effect that changing the temperature has on the position of equilibrium. Of course, we know that the equilibrium is going to shift to minimise any changes in the temperature. However, when looking at temperature, we need to think, is the forward reaction exothermic or endothermic? And the question will tell us this. Now, in this case, the forward reaction is exothermic. In a reversible reaction, that means that the backwards reaction is endothermic. Now, if we increase the temperature, the equilibrium wants to cool things back down again. So it's going to shift to the endothermic side. If we decrease the temperature, the equilibrium wants to heat things back up again. And so it's going to shift to the exothermic side. Well, what's going to happen then if the temperature is increased in the Haber process? As we mentioned, we know that that forward reaction is exothermic. This means that the equilibrium is going to shift to that endothermic direction to decrease the temperature. That means that less ammonia will be made if we increase the temperature in the Haber process. Now let's have a look at the effect that changing the pressure has on an equilibrium. When we're looking at this, we always need to look at how many gas moles we have on the reactant side and on the product side. So here I can see that in the Haber process, we have 4 moles of reactants and 2 moles of products. Now the equilibrium always wants to shift to minimise any changes. So if we want to increase the pressure, then the equilibrium wants to decrease the pressure. Now the way that it can do this is to shift to the side with the fewer moles. Now the reason for this, the example I like to think of, is imagine you're in a room with some people and the walls have started to close in. What you would want to do is to move into a room with less people. because it's going to then feel, relatively speaking, more spacious. And that's exactly what this does here. So if we increase the pressure, the equilibrium will shift to the side with fewer moles. And if we decrease the pressure, then the equilibrium will shift to the side with the more moles. So what happens if we increase the pressure in the Haber process? Well, as we said, we know we have 4 moles of reactants and 2 moles of products. So the equilibrium is going to shift to the side with the fewer moles, which is that product side. It's going to shift to the right, and we're going to end up making more ammonia. Crude oil is a finite resource which is found in rocks and is composed of the remains of an ancient biomass that was buried in the mud. Crude oil ends up being a mixture of a large number of different compounds, most of which are hydrocarbons. A hydrocarbon, this is a really important definition we need to know, is a molecule made up of carbon and hydrogen only. Make sure you remember that word only, because that's critical to getting your marks. So 2 examples of hydrocarbons we need to learn about are alkanes and alkenes. A word we're going to see described a lot throughout this topic is homologous series. So we're going to learn about alkanes, alkenes, alcohols and carboxylic acids, and all of these are examples of homologous series. Now, homologous series all have the following properties in common. They all have the same general formula. The molecular formula of successive compounds differs by CH2. They have similar chemical properties, and they have a gradual change in their physical properties. Most of the hydrocarbons found within crude oil are alkanes. The homologous series of alkanes has the general formula CnH2n+2, so make sure you remember that. We need to know the names of the first 4 members of the alkane homologous series. So these are methane, this one has 1 carbon, then we have ethane, which has 2 carbons, then we have propane, which has 3 carbons, and finally butane, which has 4 carbons. We only need to know these first 4, and notice that for the alkanes, all of the names end in ane, and the beginning is the same too, and this carries for all of the different homologous series that we will see. So we've got a little top tip of how to remember these. If you remember the phrase, monkeys eat peanut butter, then you will remember the correct order of the meth, eth, prop and bute, and therefore you'll be able to write down the correct name for the number of carbons that you need. So now let's look at this summary. So here we've got methane, which has the formula CH4. Ethane has the formula C2H6. All of these formulas are obeying that rule of CnH2n+2. Propane is C3H8 and butane is C4H10. Crude oil is a mixture of different hydrocarbons of different lengths. We can separate crude oil into fractions. Each of these contain molecules with a similar number of carbon atoms, and we can do this using a process called fractional distillation. Now this process is really important because the different fractions can be processed to produce fuels and feedstock for the petrochemical industry. So this fractional distillation of crude oil produces many fuels that get used in modern life, for example petrol and diesel oil, and these fractions can also be used to produce materials that are useful for modern life such as solvents polymers to make plastics, detergents and lubricants. Now let us look at this really important process of fractional distillation. Now the crude oil is going to pass into a furnace. When it's in this furnace, of course, it gets heated up and it's going to evaporate. It's vaporized by the furnace. Now this vapor is going to pass on into this fractionating column. Now in this fractionating column, because it's being heated from below, the bottom is hotter than the top. Now this vapor is going to rise up the column, and because it's cooler at the top, the vapor is going to cool down as it rises. This separates out these different fractions. The boiling point of the substances at the top is lower than at the bottom. So when the boiling point of the different hydrocarbon compounds get reached as it travels up this fractionating column, the hydrocarbons will condense. Once this happens, these different fractions are going to be collected. As you can see from the diagram, the liquid petroleum gases will be collected at the top because they're going to have the lowest boiling point, so they get collected up the top. Whereas things like the bitumen and the heavy fuel oil will be collected towards the bottom of this column. It's important that we know the properties of hydrocarbons with relation to the size of the molecule. So we need to know that as the molecules get larger, the boiling points increase, the viscosity also increases, but the flammability decreases. This applies to both the alkanes and the alkenes, so we should be really familiar with these properties. Combustions of hydrocarbons release energy. During this combustion process, hydrocarbons become oxidized. We need to know that the general formula for the complete combustion of a hydrocarbon is hydrocarbon plus oxygen makes carbon dioxide plus water. Let's have a look at an example of this. We could be asked to show the combustion of methane, which is CH4. In this case, we'd write CH4 plus oxygen makes CO2 plus H2O. Now though, we need to balance it. We can see that there's 4 hydrogens in the reactants, but only 2 in the products. So in order to balance these, let's double those H2Os. Now that we've done this, we can see that we have 2 oxygens in the CO2 and 2 oxygens in the water. Of course, the carbons are already balanced, so those are fine. In total, this means that we have 4 oxygens. We can balance this now by adding a 2 in front of the O2, because 2 O2s gives us 4 oxygen atoms. And so that is our balanced equation for the complete combustion of methane. Apply that process to whatever hydrocarbon you're given. During fractional distillation, the mixture of hydrocarbons in the crude oil are separated. But some of these hydrocarbons end up being much more useful than others. The shorter chain hydrocarbons are often used as fuel, and as a result, there's really a great demand for these shorter chain hydrocarbons when we compare them to the longer chain hydrocarbons. This means that we end up having too much of the longer chain hydrocarbons and not enough of the shorter chain ones to meet demand. We can solve this problem using cracking. Cracking is a process which we use to break up longer hydrocarbons into smaller, more useful hydrocarbons. So here we've got a little general formula here, and this is very, very loose because we can see it in lots of different formats. All that matters is that we have a longer hydrocarbon which gets broken down to a shorter alkane and an alkene. And what you're going to see here is this also needs to balance. So long as these rules are applied and it balances, then it is a valid equation for cracking. Now we need to know that the longer hydrocarbon has lower demand and is less useful. And the whole point of why we're cracking it is because we can make a shorter alkane, which can be used as a high demand fuel, and an alkene, which we can use to make polymers, and we can also use it as a starting material to make other chemicals. So, with cracking, we can use one of 2 methods. We can use catalytic cracking. Using this method, We vaporise the hydrocarbons, and then the vapours get passed over a hot catalyst. We can also use steam cracking. When we do steam cracking, the hydrocarbons get mixed with steam at high temperatures. Now, alkenes are more reactive than alkanes are. This means that alkenes can react with bromine water, whereas alkanes cannot. This is our test for alkenes. If we add the alkenes to bromine water, we will observe a colour change. Bromine water is normally orange, but when it's mixed together with an alkene, the alkene will decolorise the bromine water. So the bromine water will now become colourless. Now here's a little top tip which is really important. Never describe this decolorised bromine water as clear. It is not clear, it is colourless. You can have a colour and still be clear. So we never want to use the word clear to describe this. We either want to describe it as colourless or decolorised. Alkenes are hydrocarbons that have a double carbon-carbon bond within them. The homologous series of alkenes have the general formula of CnH2n. Now, alkenes are saturated molecules. This means that they have a carbon-carbon double bond, which in turn means that they have 2 fewer hydrogen atoms than an alkane would have if it had the same number of carbon atoms. Now, this table here summarises the names of the first 4 alkenes and the formulas and the structures of these. We can see that ethene is actually the first of these alkenes, not methene. And that's because we need to have 2 carbons to have this CC double bond. So we have ethene, which has 2 carbons, so its formula is C2H4. Propene has 3 carbons, so the formula is C3H6. See here that we're obeying that general formula of CnH2n. Butene has 4 carbons, so butene has the formula C4H8. And finally, pentene is C5H10. Now you can see the structures drawn here. Remember that every carbon can only have 4 bonds attached, and every hydrogen just 1 bond. This will help you when drawing these structures. Alkenes have the functional group C double bond C. And because of this bond, this functional group, we can see that alkenes react differently to alkanes. And it's this fact that enables us to identify alkenes compared to alkanes. So first, let's look at one of the reactions that alkenes do, the combustion of alkenes. Now, alkenes are more likely to combust via incomplete combustion than alkanes. That means that when they do burn, they're likely to burn with a smoky flame. When alkenes react with hydrogen, water and halogens, an addition reaction takes place. Now, addition reactions take place where atoms are added to that carbon-carbon double bond. So we break the double bond and add on new atoms. This means that we're going to form some new bonds with the reactant atoms, but also that carbon-carbon double bond will now become a carbon-carbon single bond. Let's start off by looking at the addition reaction of alkenes with hydrogen. So an alkene reacts with hydrogen to make an alkane. An example of this is the reaction of ethene with hydrogen, H2, to make ethane. And if we have a look now at the actual symbol equation, we have C2H4 plus H2 makes C2H6. And we can draw this and see what it actually looks like. So here I'm drawing ethene with its 2 carbons and its CC double bond. That's going to react with hydrogen. And what's going to happen is that double bond is going to break open. There's now a single bond between the carbon atoms. And the carbons are now able to bond to those hydrogen atoms within the hydrogen molecule. Now let's have a look at the addition reaction of alkenes with water, steam in this case. An alkene plus water makes an alcohol. This is an example of a hydration reaction. And this reaction is carried out using a temperature of 300 degrees C and a catalyst. So an example of this is the reaction of ethene with water to make ethanol. That gives us C2H4 plus H2O makes C2H5OH. Now let's have a go at writing this reaction showing its structure. Let's start by writing ethene, which has 2 carbons and that C-double-C bond. We're reacting it with water in its gaseous form. And what's going to happen is, again, that double bond is going to break open, leaving us with a C-single-C bond. And the H and the OH from the H2O bond to each of those 2 carbons. Now let's have a look at the addition reaction of alkenes with a halogen. So what we see is an alkene plus a halogen makes a halogenoalkane. This reaction is the same regardless of the halogen, so these reactions can take place with chlorine, bromine and iodine. So let's look at an example. Ethene reacts with chlorine to make dichloroethene. Let's have a look at the structure of this. Let's start off by drawing out the structure of ethene, which is a C double bond C, and then we want to add on Cl2. Now we know that to do this, we're going to break open that double bond, leaving us with a C single C bond, and attaching to each of those 2 carbons a Cl coming from that chlorine molecule. Alcohols contain the functional group OH. Now the homologous series of alcohols can be represented in the form of something like CH3OH, or we can draw out its structure. Now we also need to know the names of the first 4 members of the alcohol homologous series. Now this follows the exact same pattern as all of these other homologous series. When we have a 1-carbon alcohol, it's called methanol. When we have a 2-carbon alcohol, it's called ethanol. 3-carbon is propanol, and 4-carbon is butanol. Again, we can prompt ourselves with our monkeys eat peanut butter. Now, we'll notice here that when we have an alcohol, the name ends in anol. So make sure that you learn that that is our ending of these names. This table here summarises the names of the first 4 alcohols, their molecular formula and their structure. And we can also see some of their uses. So let's run through these. Methanol can be used as chemical feedstock, and it's also added to industrial ethanol to stop people drinking it because it's toxic. Ethanol, on the other hand, is the alcohol used in alcoholic drinks. It's also used as a fuel and as a solvent. Now, propanol and butanol can also be used as both fuels and solvents. We need to know a series of different reactions that alcohols can undertake. The first one is combustion reactions. We need to know that an alcohol plus oxygen makes carbon dioxide and water. So in this case, we could look at ethanol plus oxygen makes carbon dioxide and water. Now, complete combustion occurs when we have an excess of oxygen. If we have a limited supply of oxygen, then incomplete combustion will take place instead. During incomplete combustion, we still make our water, but carbon or carbon monoxide will get made instead of that carbon dioxide. We need to know that shorter alcohols will combust more easily, and this makes them more efficient fuels. Now, shorter alcohols will combust with a blue flame and will release lots of energy. The next reaction that we need to know for alcohols is that if an alcohol reacts with sodium, we will make sodium alkoxide and hydrogen. So if we look at an example here, if we had ethanol plus sodium, we'd make sodium ethoxide and hydrogen. Now, when we add sodium to an alcohol, we will observe bubbles of gas forming, or we might call it effervescence, and that's due to the hydrogen gas that gets formed in that reaction. Alcohols get oxidized by combustion. However, we also need to know that they can also be oxidized using an oxidizing agent. Alcohols will react with oxidizing agents to form carboxylic acids. An example of an oxidizing agent that we use in chemistry is potassium dichromate. So this is our general equation here. Alcohol plus an oxidizing agent makes a carboxylic acid and water. If we look at a specific example, if we had ethanol plus an oxidizing agent, we would make ethanoic acid plus water. Looking at the balanced equation here, you can see that when it comes to writing an oxidizing agent, we just use a square brackets O. That's important that we know that that represents our oxidizing agent. We also need to know about the solubility of alcohols. Short-chain alcohols, such as methanol, ethanol and propanol, are all soluble in water. However, as the length of the alcohol chain increases, alcohols become less soluble. So we need to make sure that we know this trend. Finally, we need to know that we can make ethanol by fermenting glucose. Ethanol, of course, is an alcohol. It's found in alcoholic drinks like wine and beer, and it can also be used as a fuel for vehicles. For these reasons, it's something that we often want to make industrially. We need to know that fermentation uses yeast and anaerobic conditions, so without oxygen, to make ethanol from glucose. So the overall equation here is that glucose will be fermented to make ethanol plus carbon dioxide. Now we need to know that we need the following conditions to carry out fermentation to make ethanol. We need sugar or glucose dissolved in water. We need to have some yeast. We also need anaerobic conditions, so we need an absence of oxygen. And we need temperatures between 25 and 35 degrees C. Now the reason why these temperatures are so important is because yeast contains enzymes. If the temperature was too low and it was very cold, then fermentation will happen very slowly, to the point it might even stop. However, if the temperatures are too high, then we have a different problem. The enzymes will denature, and this will also stop fermentation. So we need to make sure we stay within that sweet spot of 25 to 35 degrees C. Carboxylic acids contain the functional group COOH. The homologous series of carboxylic acids can be represented in the form of something like CH3COOH, so with that COOH at the end of its formula, or using this particular structure which shows a C double bond O and then an OH also attached to that carbon. We also need to know the names of the first four members of the carboxylic acid homologous series. So the names of the carboxylic acids end with anoic acid, and they begin with meth, eth, prop and bute, just like all the other ones. So a 1-carbon carboxylic acid is called methanoic acid, a 2-carbon carboxylic acid is called ethanoic acid, 3-carbon is propanoic acid, and 4 carbons is butanoic acid. This table here perfectly summarises the first 4 carboxylic acids together with their molecular formulas and their structures. Carboxylic acids, we know, have a pH less than 7 when dissolved in water. Carboxylic acids are weak acids, not strong acids. And the reason why they're weak acids is because they only partially ionize or dissociate in water. Now it's important that we know some of the different reactions of carboxylic acids. Now carboxylic acids, actually, they're acids, aren't they? So they will undergo the same reaction as other acids with metals, bases and carbonates. So if we had a metal reacting with an acid, we'd still make a salt and hydrogen if it was a carboxylic acid. If we had a carboxylic acid reacting with a base, we would still make a salt and water. And if we had a carboxylic acid reacting with a carbonate, we'd still make a salt, carbon dioxide and water. The main difference that we'll see here is that we end up making carboxylate salts when we're using a carboxylic acid. For instance, if we had sodium reacting with ethanoic acid, the salt we would make would be sodium ethanoate. Finally, we need to know that carboxylic acids react with alcohols to form esters. Esters have the functional group COO, and the general formula for the formation of an ester is an alcohol plus a carboxylic acid makes an ester plus water. Now the one reaction that they could ask you about is that ethanol plus ethanoic acid makes ethyl ethanoate plus water. Now let me show you what that reaction looks like. So let's start off by drawing ethanol. Remember, ethanol has 2 carbons and it has the OH functional group. So once we've finished drawing that, I'm going to draw ethanoic acid, and I'm going to draw it so that the carboxylic acid functional group faces that alcohol. All will become clear. So again, ethanoic acid has 2 carbons. See here that the H from the OH and the OH from the carboxylic acid can react together to form water. Now that water gets removed in this reaction, and we combine these 2 parts together. So this O is going to join together with this C double bond O. And this gives us our ethyl ethanoate structure, plus the water that got removed in that reaction. Now esters like this ethyl ethanoate are used as solvents, flavourings and perfumes, and you'll find that they have a fruity smell. Alkenes can be used to make polymers using addition polymerization. So a couple of examples of addition polymers are polyethene and polypropene. As you can see, we just stick poly in front of the name of that alkene. In an addition polymerization reaction, many small molecules will join together to form a very large molecule, that polymer. Here we can see that reaction taking place. So we have ethene here, and it will become the polymer polyethene. Notice here in this diagram, we can see that our double bond has broken open, and it is now a single bond with 2 open arms. Now those open arms would be connected to other repeat units, okay? So it's to show that this just repeats and repeats and repeats and repeats. And this is why we call this a repeat unit. Now that little N down here represents a large number of molecules. So if we had 100 ethenes, then that would be a little 100, to show that we have 100 of these repeat units in a row. Now the small molecules are called monomers, and the large molecules that they form are called polymers. Now we'll notice as well that this repeat unit of an addition polymer has the exact same atoms as the monomer that formed it. And that's because that polymer was the only product in these reactions. This table here shows some examples of addition polymers. Here we've got the monomer ethene. If we wanted to show the formation of polyethene, all we would need to do is open up that double bond, open up its arms, put the H's above and below those carbons, and then do your brackets around it. Let's do it for propene now. Propene has 3 carbons and just the 1 double bond. So here I am drawing it in this particular way. And when we have propene forming polypropene, again, we just open up that double bond, open up the arms, and put everything else above and below those carbons, and then throw in the brackets as well. I hope you can notice a pattern here. So let's try one that you've not seen before. This is chloroethene. So here it has, and you're not expected to know this, it has 2 H's on the first carbon and an H and a Cl on the other. But just notice here we can apply the same principles. Double bond that's in the middle, we just open up the arms and we put 2 H's above and an H and a Cl below those carbons, and again throw in the brackets at the end. Condensation polymers are formed using monomers with 2 different functional groups. Now these functional groups will end up reacting together and losing a small molecule such as water. Now this is why we call these reactions condensation reactions. So 2 typical types of molecules that would react together to form condensation polymers include diols and dicarboxylic acid. Now all that a diol is a molecule that has 2 alcohol groups. And a dicarboxylic acid is just a molecule that has 2 carboxylic acid groups, as you can see in these diagrams. Now we will sometimes see the middle parts of these molecules represented with a simple shape, such as a rectangle. And the whole point of this is it just simplifies things. Rather than you at GCSE having to draw these complicated molecules, you can just cut out the middle bit and use a shape. Now, diols and dicarboxylic acids can react together to form polyesters. And what will happen is the OH group of the diol will react with the OH part of the carboxylic acid group, and we will form water. See what's happening here? We are going to remove the water. And this in turn will form this bond here. That is our ester bond. And here you can see we've removed one molecule of water. Now this is just one reaction. We don't yet have a polymer, but this reaction would go on and on and on to form a polymer with lots more alternate diols than carboxylic acid, diol, carboxylic acid repeating. And this is what our general equation would look like. Here we have our diol. If we had n of those, we could react it with n of the dicarboxylic acid. We would make our polyester, and we would make 2NH2O. So that would be our general reaction. And that is how we make condensation polymers. Amino acids have two different functional groups. As you can see here, they have an NH2 group, and they also have a carboxylic acid group. Now, amino acids will react together via a condensation reaction to form polypeptides or proteins. During a condensation reaction, water gets removed and a bond gets formed. Now, one specific type of amino acid is called glycine. Glycine molecules can react together to form polyglycine, a polymer. So here this general formula shows this. If we had N glycines, they would react together via a condensation reaction to form polyglycine and N waters. Now we'll notice there that for every extra monomer added, every extra glycine in this case, an additional water molecule gets formed. Now this is one example. There are actually many different types of amino acids, and different amino acids can all be combined in a chain together to make a protein. DNA, or deoxyribonucleic acid, is a large molecule which is essential for life. Now, DNA contains genetic instructions. These are the codes needed for the development and functioning of all living organisms and viruses. DNA molecules consist of two polymer chains, which are made up of 4 different monomers called nucleotides, arranged in a double helix. This table here gives us a great summary of the biological polymers that you need to know about. We need to know that DNA is a naturally occurring polymer, whose monomer are the nucleotides. And we need to know that DNA provides the instructions needed for every living organism to stay alive. Next up, we've got proteins. We need to know that the polymer of proteins, or polypeptides, have the monomer of amino acids. And proteins have many roles, including making enzymes and making hormones. Next up, we've got starch. The monomer for starch is a sugar, and the role of starch is that it stores energy in plants. Finally, the last naturally occurring polymer that we need to know about is cellulose. Cellulose, you may remember from biology, is used to strengthen cell walls in plant cells. The monomer for cellulose, just like starch, is a sugar. In chemistry, we need to understand what is meant by a pure substance. So a pure substance is a single element or compound which has not been mixed with any other substance. Now, you might find this is a bit different to our everyday language. We might use the word pure as we speak about things such as milk may be pure because it doesn't have any additional substances added to it. However, chemically, it is a mixture of different substances. There's fat molecules, there's water, all mixed together. However, in chemistry, we park that understanding and we now just think of it as that single element or compound that hasn't been mixed with any other substance. So we need to know that pure elements and compounds melt at specific temperatures. And we can distinguish between pure substances and impure substances using the following method. So we want to measure the melting point. Pure substances are going to have a sharp, very defined melting point. For instance, water has a melting point of 0 degrees C. However, impure substances are going to melt over a broader range of temperatures. So if you're ever given a range of temperatures for a melting point, you know that that substance is an impure substance. Formulations are something that we actually use all the time. Formulation is a mixture that has been designed as a useful product. So examples of formulations include fuels, paints, medicines, foods, fertilisers, cleaning agents and alloys. You can see that we have so many uses for these formulations in our day-to-day lives. So we need to know, how do they get made? We need to know that to make a formulation, we need to mix together components that have a particular purpose in carefully measured quantities to ensure that the product has the properties required. Chromatography is a method that can be used to separate mixtures. And it can be really useful when we want to attempt to identify certain substances. So, as you can see in this diagram, we often use chromatography paper and a pencil line. We put some dyes or whatever substances we're looking to examine along this pencil line and place it into a solvent. Now, chromatography uses two different phases that we'll hear about in the exams that we need to be familiar with. So the mobile phase is the solvent, which is going to carry the different substances. This could be water, for example. The stationary phase, on the other hand, is the non-moving phase. In this case, that could be the chromatography paper. So in carrying out this chromatography, we can calculate an RF value that will be used to identify unknown substances. All different substances will have their own unique RF value. So the way that we work out the RF value is we get out our ruler and we measure the distance moved by the substance. So that will be from that pencil line up to the point where that dot has moved. And then we divide it by the distance moved by the solvent. And that again is going to be moving from that line up to the maximum distance that it has moved. And it should make that clear in the exam where the solvent's moved to. So remember, we're just going to use our ruler. Make sure you're consistent with using centimetres or millimetres for both measurements. It doesn't matter which one you choose. And then pop it into the equation and you'll get the RF value, which will always be a number between 0 and 1. Now we need to know that the RF value might change in a different solvent. So if we use water one time and say ethanol another time, we may get a different RF value. So mixtures are going to separate into different spots. So here you can see this shows a mixture because we've got two different spots. However, pure compounds like this one here produce a single spot, and that will be true in all of the solvents. It will always only produce a single spot. If we ever need to test for hydrogen gas, we want to hold a lit splint at the open end of a test tube containing that gas, and if hydrogen's present, we will hear a squeaky pop sound. To test for oxygen gas, we want to hold a glowing splint inside a test tube containing a gas you want to test. Now by glowing splint, we mean that it was lit, but then we blew it out and it's still glowing. Now if oxygen is present, then that glowing splint will relight. We need to know how to test for carbon dioxide gas. So what we want to do is to bubble the gas through an aqueous solution of sodium hydroxide, or more simply we could say that we need to bubble it through lime water. If carbon dioxide is present, then the lime water will turn milky or cloudy in colour. To test for chlorine gas, we want to put damp blue litmus paper into the gas, and if chlorine was present, the litmus paper will be bleached and it will turn white. Sometimes we might need to identify some metal ions in a solid substance. To do this, we can use a flame test. So the method for this is we want to dip a clean wire loop into a solid sample that we're trying to test. And then once we've done that, we're going to pick up the loop and we're going to put it in a blue flame on a Bunsen burner. Now what we're going to do is observe the flame colour, because what we're going to expect to see here is the flame will change colour if certain ions are present. Now these are the results that we need to know. So it's only these 5 different metal ions that you need to know their flame colours. So lithium, the Li+ ion, will give you a crimson flame. Sodium, Na+, gives us a yellow flame. Potassium, or K+, gives us a lilac flame. Calcium, or Ca2+, gives us an orange-red flame. And finally copper, which is Cu2+, gives us a green flame. Now occasionally a problem will pop up when trying to identify metal ions. So there's a good chance that some samples might have a mixture of different ions within them. And as you know, with paint and so on, if you mix together different colours, then you can't see the original colours anymore. And so this can mask certain flame colours. Imagine if we had like an orange-red calcium ion as well as a crimson lithium ion. The orange-red and the crimson are going to hide each other, and we won't necessarily be able to identify them both. So we need to know that that's one of the main problems that can arise during a flame test. When we have metal ions in a solution instead, we can't use a flame test. Instead, we're going to use this sodium hydroxide test. So to test for metal ions in solutions, we add sodium hydroxide to our solution that we're testing. And then if a certain metal ion is present, we will see a precipitate form. And the colour of that precipitate will enable us to identify it. Now here there are 6 different metal ions in solution that you need to be able to identify here. So as you can see here, we've got aluminium, and when that reacts with sodium hydroxide, we form aluminium hydroxide, which is a white precipitate. Now here you can see this ionic equation, and all of these reactions have ionic equations. I don't want you to freak out that there's so many different ones. Instead, I want to quickly show you the pattern that we see here. All of them involve that metal ion with its relevant charge. And then you plus on as many hydroxide ions, so OH- ions, as you had that charge. So aluminium is aluminium 3+, and then we add 3 OH-. And then you form Al and in brackets OH, and again with that 3. Notice all of the rest of these is exactly the same. So actually you don't need to learn 6 different reactions here, just learn the pattern. Again here we've got calcium 2+ plus 2 OH- makes calcium OH2. So just spot that pattern, and also notice that the state symbols tell us we have an aqueous plus an aqueous makes that solid for the precipitate. Calcium also reacts with sodium hydroxide to form a white precipitate, this time of calcium hydroxide. Magnesium also reacts with sodium hydroxide to form a white precipitate, this time of magnesium hydroxide. Now copper 2, and that Roman numerals tells us the charge of the copper ion, is going to react with sodium hydroxide to form a blue copper hydroxide solution. Iron 2+ reacts with sodium hydroxide to form the green iron 2 hydroxide solution. and iron 3 will react with sodium hydroxide to form the brown iron 3 hydroxide. Now it's very important that you go away and you learn these different colours that are formed, as well as these ionic equations. Now you would have noticed that aluminium, calcium and magnesium all react with sodium hydroxide to form a white precipitate. Now that's going to cause issues when we're trying to do these tests to identify what ions we have present. How will we know if it's aluminium, calcium or magnesium? Well, there's one key additional fact here that's going to help us. If we add more sodium hydroxide so that we have an excess of sodium hydroxide, only the aluminium hydroxide precipitate will dissolve again. So that's one way that we could positively identify aluminium hydroxide. If we add a little sodium hydroxide, we get a white precipitate form, and then if we add more, we'll notice that it will disappear and dissolve back into the solution, whereas calcium hydroxide and magnesium hydroxide won't. To test for carbonate ions, we want to react the carbonates with a dilute acid. Now, we should know that when carbonates react with acid, we form carbon dioxide gas. Now, this gas we can bubble through lime water, and if the carbonate was present and carbon dioxide was formed, the lime water will turn milky or cloudy in colour. And this confirms the presence of carbon dioxide and therefore a carbonate in the original solution. We need to know how to test for halide ions. And in this exam, we only need to know about the Cl-, the Br- and the I- ions. To test for these ions, we have to first add nitric acid and then add silver nitrate to our solution. Now, if those halide ions are present, we're going to get a different precipitate formed, dependent on the halide. If chloride ions were present, they would react with silver nitrate to form silver chloride. This is a white precipitate. The ionic equation for this is Ag plus aqueous, which is the silver ions, plus Cl minus, those chloride ions, which are aqueous, and they go on to form AgCl solid, which is the precipitate. Now, if bromide ions were present, they would react to form silver bromide, which is a cream precipitate. The ionic equation is almost exactly the same. We just replace the Cl minus with Br minus, and AgCl becomes AgBr. And then for the iodide ions, the iodide will react with silver nitrate to form silver iodide, which is a yellow precipitate. And the ionic equation here is just Ag plus aqueous plus I minus aqueous makes AgI solid. But again, with those ionic equations, don't think that they're three separate equations that makes things so complicated. Just notice how similar they are and notice the pattern that you can see forming there and just learn that. And in addition to that, when looking at these observations, notice as you go down the group from chloride to bromide to iodide, the colour is getting kind of grimier. It's going from white to cream to yellow. So just remember that trend in the colours as well, as it will help you get them in the right order. To test for sulfate ions in solution, we want to add a barium chloride solution and dilute hydrochloric acid. Now, if the sulfate ions are present, then a white precipitate will form. The ionic equation for this is Ba2 plus aqueous plus those sulfate ions, which are SO4 2- aqueous, will form barium sulfate, BaSO4 solid. Now it's that barium sulfate that gives us that white precipitate. Chemical tests can be really helpful. However, elements and compounds can also be detected and identified using instrumental methods. And there's a lot of advantages of using instrumental methods compared with these chemical tests. One is that they're very accurate. Imagine the test for halide ions. You've got a white precipitate or a cream precipitate or a yellow precipitate. It could be very reasonable to assume you could misjudge those colours. However, an instrumental method wouldn't do that. Instrumental methods are also very sensitive. They can detect even very, very small amounts, which perhaps our chemical tests couldn't pick up on. They're also very rapid. We just pop them in the machine and they can immediately identify what we have. And those are our 3 advantages that we need to know. The instrumental method that we need to know about in a little bit more detail is flame emission spectroscopy. Now, flame emission spectroscopy is an instrumental method used to analyse metal ions in solutions. So we could use it instead of those sodium hydroxide tests. We need to know how flame emission spectroscopy works. So to start off, a sample is put into a flame. So the light given off by this flame is passed through a spectroscope. And this spectroscope gives a line spectrum that can be analysed to identify the metal ions in the solution. Now we can also use this data to work out the concentrations of the metal ions in solution too. So we get extra information here in addition to that identification. So make sure that you've got a good idea of how flame emission spectroscopy works. You don't need to know too much detail, just what I've said here, and then you should be able to answer any question that comes up. For the past 200 million years, the composition of the atmosphere of the Earth has been roughly the same. We have about 80% nitrogen, about 20% oxygen, and small proportions of other gases, including carbon dioxide, water vapour, and the noble gases as well. We need to know about how the Earth's atmosphere has evolved. So we need to know what the Earth's early atmosphere was like in the first billion years of the Earth. So we need to know that initially we had a lot of volcanic activity. And as these volcanoes erupted, they released gases which ended up forming this early atmosphere. Nitrogen was released by these volcanoes and it ended up building up in the atmosphere. Water vapour was released by these volcanoes as well, but it ended up condensing and formed the oceans. The early atmosphere of the Earth was mostly made up of carbon dioxide, and there was little to no oxygen present. We think that back in those first billion years, as well as all these other gases, there were also small amounts of methane and ammonia present in the early atmosphere. Now, as the oceans formed when that water vapour condensed, the carbon dioxide that was present in the atmosphere ended up dissolving in the water, and carbonates formed, producing sediments under the ocean. Now, this reduced the amount of carbon dioxide in the atmosphere, bringing it down, and we're now on the way to forming our modern atmosphere. Over time, the carbon dioxide levels came down and the oxygen levels increased. Now, we need to understand why the oxygen levels increased. We should understand that plants and algae began to evolve. And as they evolved and grew, they produced oxygen by photosynthesis. Now, the algae first started producing oxygen as far back as 2.7 billion years ago. So a really, really long time ago. The algae were there first, and over time, plants evolved. And as the plants started to grow, even more oxygen was being put out into the atmosphere because even more photosynthesis could happen. Now, this continued until eventually the oxygen levels had got so high that we could support the evolution of animals, which of course need a lot of oxygen to respire, to grow and to move. So eventually it ended up coming to this 20% of oxygen in the atmosphere which we currently have now. Now that process of photosynthesis of the algae and the plants also had the knock-on effect of decreasing the proportion of carbon dioxide in the atmosphere. So this is one of the main ways in which carbon dioxide levels went down over time. Other ways that the proportion of carbon dioxide decreased was due to the formation of sedimentary rocks such as limestone, and also the formation of fossil fuels such as coal, crude oil and natural gas. Greenhouse gases are gases that are actually really important to have in our atmosphere. Without the presence of greenhouse gases, the Earth would actually be too cold to support life. However, the problem arises when there's too many greenhouse gases present. When we have too many greenhouse gases in the atmosphere and they're too abundant, what will happen is the temperature of the Earth will be increased too much. Now, we need to know the names of 3 greenhouse gases. We need to know carbon dioxide, methane, and water vapour. We need to be able to explain how the greenhouse effect works. And this is exactly the same reason why in a greenhouse it gets hot on a sunny day, or if you're in a car and all the windows are up, again it gets really hot in there on a hot day. So let's understand why this greenhouse effect happens. So we need to know that electromagnetic radiation from the sun radiates out and passes through the Earth's atmosphere. Now this electromagnetic radiation that's coming from the sun includes a range of wavelengths, including some shorter wavelength and some longer wavelength. Now the Earth is going to absorb most of this radiation that comes through the atmosphere, and the Earth is going to get warmed up. Now this warmer Earth is going to radiate a longer wavelength, infrared radiation. Now some of this radiation can go back into space, but some of this infrared radiation will get absorbed by the greenhouse gases in the atmosphere. Now it's this process here that increases the temperature of the atmosphere. Human activities have a direct effect on the amount of some of the greenhouse gases that get released into the atmosphere. So if we first think about carbon dioxide, the amount of carbon dioxide in the atmosphere can get increased by several human activities. These include the burning of fossil fuels in vehicles and factories, and deforestation. Now let's think about the amount of methane in the atmosphere. This is increased by cattle farming and paddy fields or rice farming. So we need to be able to answer the question, are humans causing climate change? Most scientists believe that the human activities causing the surface temperature of the Earth to increase. Now the evidence that they've used to form these beliefs have come from peer-reviewed evidence. However, climate change is very complex, so scientists can't be certain of this despite all these peer reviews. We need to consider the fact that maybe we're oversimplifying some of the models that we're using to come to these conclusions. We need to consider that people's opinions and speculations may cause biases. And also, we might have certain biases from certain companies that might commission the research. We need to always think about where this information has come from, who has paid the money for this research, and if they actually have an ulterior motive to come to a certain conclusion. We also need to think about the quality of the evidence and also some uncertainties that might arise from measurements that have been taken and other factors as well. We need to know what is meant by climate. Now, climate refers to the average temperature and weather cycles over a long period of time. Climate is different to weather, which is talking about the temperature and the weather now. So the climate of Earth has always actually been changing. This isn't a new thing. The climate of Earth has cycled between periods of extreme cold, which are the ice ages that have happened in the past, and also warm periods as well. Now, these used to just be naturally occurring phenomenon. They could have been caused by things such as volcanic eruptions and changes that are occurring on the sun. However, when we talk about global warming, this is different to climate change. When we refer to global warming, we're referring to the warming of the climate that has occurred due to human activities over the last 200 years. So we're just looking at recent times when we're talking about global warming. This graph here is a very important one, and it shows the relationship between the change in carbon dioxide concentration over the last few hundred years and the temperature. Here you can see that as the carbon dioxide concentration has increased, the general trend is that the temperature has also increased. We can see here that there's a strong correlation between the Earth's average temperature and the concentration of carbon dioxide in the atmosphere. An increase in the average global temperature is a major cause of climate change. We need to know some of the effects of global warming. So these include glaciers melting, droughts, sea levels rising, and also the loss of habitats. A carbon footprint is the total amount of carbon dioxide and other greenhouse gases emitted over the full lifetime of a product, event, or service. We can reduce the carbon footprint by reducing the emissions of carbon dioxide and methane. So if you think of some examples of how we can reduce our carbon footprint, this can include using solar power instead of fossil fuels, cycling or walking to work or school instead of driving. We can fly less and holiday more locally. And also planting trees is another great way that we can reduce our carbon footprint. The combustion of fuels is a major source of the pollutants within the atmosphere. We need to know that fuels may contain carbon, hydrogen, and also sulfur. Now, when we combust these fuels, we can release the following gases into the atmosphere. So we might release carbon dioxide, water vapour, carbon monoxide, sulfur dioxide, oxides of nitrogen, and particulates. Let's have a look in a bit more detail at the process of complete combustion. Now, complete combustion occurs when a hydrocarbon fuel is combusted in an excess of oxygen. And the general equation for complete combustion is fuel plus oxygen makes carbon dioxide and water. Now, an example of this is methane fuel plus oxygen makes carbon dioxide and water. We need to make sure that we can write the balanced symbol equation for these equations too. So make sure you're familiar with the formula of the alkanes. Make sure you know the formula of oxygen, carbon dioxide and water, and you're happy balancing these equations. Now, the great thing about complete combustion is that we release the maximum amount of energy. Downsides, though, are that we release carbon dioxide, which is a greenhouse gas, and water. Now, however, let's have a look at incomplete combustion. Now, incomplete combustion occurs when a hydrocarbon fuel is combusted, this time in a limited supply of oxygen. Now, this releases much less energy than complete combustion, and instead of releasing carbon dioxide, you're going to find that carbon monoxide and or particulate carbon are going to be produced. Now, whether you produce carbon monoxide and carbon, or just carbon monoxide, or just carbon, or some other combination, is going to be dependent on how much oxygen we have available. So let's have a look here at the incomplete combustion of ethane in oxygen. So here we've got ethane plus oxygen, and here we're saying we'll make carbon monoxide and water. Now again, we need to be able to balance this, so make sure you know that the formula for carbon monoxide is CO, and the formula for particulate carbon is just C. So we need to know that carbon monoxide is a poisonous gas. And what makes it so dangerous is it can bind to hemoglobin in the blood and prevent oxygen from binding. Now this will lead to death. Now the problem with carbon monoxide, which makes it particularly dangerous, is that it is a colourless and odourless gas. which means it's an invisible, silent killer. So I'm using this as my opportunity to remind you that if you have a little fire or a campfire, make sure it is well ventilated. Don't ever put it in a tent or something like that where it would have poor ventilation, because there can be tragic consequences. So next up, we've got particulate carbon. Now that is the carbon or the soot that can get released during incomplete combustion. This can be seen as a black smoke coming off, and the problem with this is it can worsen asthma and it can also cause global dimming. So make sure you know the dangers of carbon monoxide and carbon, and the fact that we make less energy also during incomplete combustion. We need to know where each of these atmospheric pollutants are made. So carbon dioxide is made during the complete combustion of a carbon-containing fuel. Carbon monoxide is made during the incomplete combustion of a carbon-containing fuel. Sulfur dioxide is made during the combustion of a fossil fuel that contains sulfur impurities. Oxides of nitrogen, such as nitrogen monoxide and nitrogen dioxide, are made during the oxidation of nitrogen in the air inside a vehicle's engine. And carbon particulates, or soot, are made during the incomplete combustion of a carbon-containing fuel. Some fossil fuels contain sulfur impurities. Now, when we combust these fuels, we're going to find that that sulfur is also going to get oxidized. So we're going to have the reaction take place that says that sulfur plus oxygen makes sulfur dioxide. Now this sulfur dioxide is going to get released into the atmosphere, and what we'll find is that it's going to get further oxidized and it will end up making sulfur trioxide. And this is because the sulfur dioxide plus oxygen makes sulfur trioxide. Now it's this sulfur trioxide that can dissolve in the rainwater. And when that happens, we make dilute sulfuric acid, which forms acid rain. Now, acid rain is particularly harmful to aquatic plants and animals because that acidic rain will go into these bodies of water, such as lakes, and change the pH, making it more acidic. Now, this upsets that perfect balance of that ecosystem, and it can lead to plants and animals dying. Another issue with acid rain is it can damage buildings and statues. If the buildings and statues are made from rocks such as limestone, which is a carbonate, calcium carbonate, what will happen is that will react with the acid, turning to salt, water and carbon dioxide. This erosion can lead to damage to these statues and buildings. We should know that the atmosphere is made up of approximately 80% nitrogen and 20% oxygen. Car engines where combustion is taking place can reach very high temperatures and pressures. Now this can lead to the nitrogen and the oxygen that are present in the air reacting together to form oxides of nitrogen. Now in car engines, we'll find that the most common oxides of nitrogen that are made are nitrogen monoxide and nitrogen dioxide. It is common that you'll see these oxides of nitrogen referred using the general formula NOx. Now, these oxides of nitrogen can be dangerous. They can cause photochemical smog and breathing difficulties in humans, such as asthma. So it's important that we minimise the presence of these oxides of nitrogen in the atmosphere. This table here shows a summary of the problem with the different atmospheric pollutants. Carbon monoxide is a toxic or poisonous gas, and it is colourless and odourless, which makes it hard to detect. Sulfur dioxide causes acid rain. Oxides of nitrogen cause respiratory problems in humans, like aggravating their asthma, and it also causes photochemical smog. Whereas particulates, which is that carbon particulates or soot, they cause health problems in humans and also global dimming. Humans use the Earth's resources for many different things. These include food, shelter, transport and warmth. And humans also use natural resources, but supplemented by agriculture, farming, to provide food, fuels, clothing and timber. There are also many finite resources from the Earth, the oceans and the atmosphere that we process to provide energy and materials. Now we need to know what a finite resource is. And a finite resource is a resource which will eventually run out. And a good example of this is fossil fuels. So we use up fossil fuels at a faster rate than we can form new fossil fuels. This means it will eventually run out and it is a finite resource. Now, chemistry has a really important role in improving industrial and agricultural processes to make sure that we can sustainably develop new products. We also need to know what is meant by sustainable development. This is a word that gets used in chemistry quite a lot, and a lot of people don't really realise what it means. Sustainable development is a development that meets the needs of current generations, so it ensures they get what they need, but without compromising the ability of future generations to meet their own needs. So if we were just to quickly use up all the fossil fuels because we need energy now, and we're not thinking about future people, then that would not be sustainable development. So make sure you know your definition for sustainable development. Potable water is water that is safe to drink. Now for humans, potable water must have low levels of dissolved salts and microbes, and that's what makes it safe. Now both wastewater and groundwater will need to be treated before they're safe to drink. Now in the UK, most of the potable water gets produced from fresh water, whereas in other places, potable water is produced from seawater. We need to know how we obtain potable water from fresh water. Well, our first step is we need to choose an appropriate source of water. Once we've done that, we're going to pass the water through a series of filter beds. The purpose of this is it's going to remove any large objects, perhaps like branches, and other insoluble molecules. Finally, once we've done this, we're going to sterilise the water. We'll do this either using UV light, chlorine or ozone. And the reason for this is it's going to kill any microbes that may be present. Now let's have a little comparison of the different types of water that there are. Pure water is composed of water molecules only. There's nothing else in it except H2O. Then if we think about seawater or other salty waters, there are water molecules present, of course, but there's also very high levels of salt and potentially high levels of microbes. Now if we think about fresh water of course has water molecules. It will likely have low levels of salt, but it's going to have potentially high levels of microbes. Finally, if we think about potable water, it's going to have water molecules in it. It's safe for it to have low levels of salt, and also it can have safe levels of microbes within it. So it's not going to really be water molecules only, it's not pure water necessarily, but it needs to have safe levels of salt and microbes to be drinkable. In certain places like the UAE, freshwater supplies might be limited, but there might be an abundance of seawater. Now in these cases, we may need to desalinate or remove the salt from the seawater to obtain the potable water. Now desalination can be carried out using either distillation, where we heat up the salt water, the water will evaporate and then condense, and you've separated the water from the salt. Or we could use reverse osmosis. Reverse osmosis involves the use of membranes to separate the salts from the water. Now, the problem with desalination is that these processes require a large amount of energy. Therefore, this is an expensive process, and it's only really going to be practical if this is your only option and if you have a lot of money to spend on these processes. Large amounts of wastewater get produced by urban lifestyles and industrial processes. Now, this wastewater needs to be treated before it can be released back into the environment. We need to know that with sewage and agricultural wastewater, we need to remove organic matter and harmful microbes. Whereas with industrial wastewater, which comes from factories, we need to remove organic matter and harmful chemicals. Now, when we need to treat sewage, we have to go through the following steps. Firstly, we need to do screening and grit removal. These processes are going to remove large particles. Next up, we've got to do sedimentation. Now, this process allows the solid sediments to settle to the bottom. Now, this forms sludge, and remaining liquid we call effluent. Now, this sewage sludge that's now separated from the effluent can be treated separately. The sewage sludge will get anaerobically digested, so without oxygen, by specific anaerobic bacteria. This forms biogas, which we can then use as a fuel. And at the same time, of course, we've broken down that sewage sludge. Now, the effluent, on the other hand, is treated with aerobic bacteria, so bacteria that will respire using oxygen. This breaks down the effluent. We will then remove the bacteria, and the water is now safe enough to release back into the environment. The availability of metal ores in the earth are limited. This means that scientists have to come up with new methods of extracting the metals from lower grade ores. So they've got two methods that they use for this. They've got bioleaching and phytomining or phytoextraction. So let's have a look at bioleaching first. What is bioleaching? Bioleaching is using bacteria to produce acidic leachate solutions which contain metal compounds. Now, once we obtain this metal compound, we can process it to extract the metals. Now let's have a look at phytomining. So phytomining is using plants to absorb metal compounds. So this process of phytoextraction involves growing plants in a soil which contains that low-grade ore. Then as the plants grow, they're going to absorb the metal ions through their roots. As a result, they're going to accumulate the metal ions within their cells. So as they grow and get bigger, we will eventually harvest them and then burn them. Now when we burn them, we're going to have some ash left over, and that ash is going to contain the metal compounds that we can process and extract the metal from. We need to make sure we can compare the processes of bioleaching and phytomining and know what the advantages and disadvantages of them both are. So bioleaching has a great advantage of not requiring any high temperatures. However, it does produce some toxic substances such as sulfuric acid, which can be harmful for the environment. Phytomining, on the other hand, is very useful because it can conserve high-grade ores, and it reduces the need for mining, and it also reduces the need to dispose of rock waste. However, some disadvantages of it is that it's quite slow because, of course, we need to nurture these plants, grow them to a good size, before we can then burn them and extract the metal. Life cycle assessments are assessments that can be carried out to find the environmental impact of a product, such as a paper cup, a service, or an event. And life cycle assessments have 4 different stages. So we want to look at the extraction and processing of the raw materials. We need to have a look at the manufacturing and packaging process. We need to have a look at the use and operation of this product during its lifetime. And we also need to look at how it gets disposed of at the end of its useful life, if it is indeed a product. So at each of these stages, our life cycle assessments are going to have a look at what raw materials are used. This can include water, the amount of energy used along the way, and what waste substances have been released into the environment. Many materials, including metals, glass, clay ceramics, plastics, they're all made from limited raw materials, which means that they can eventually run out. Now, obtaining the raw materials from the earth by mining and quarrying is problematic because it uses a lot of energy and it can also damage the environment. So for these reasons, it's really important that we find ways to reduce the use, to reuse and to recycle materials. Now let's think about glass and metals and how we can reduce the use of resources for those. Well, with glass, we can always recycle it. When we recycle glass, the glass gets crushed and melted so that we can then reform it into different products. With glass, we can also reuse it. Of course, if we had a glass bottle or a glass jar, we could reuse it and not just throw it away after one use. And metals as well, we can of course recycle those as well, and we would do this by melting them and then recasting them or reforming them into different products. Metals can oxidize in air, and this is because the metal reacts with the oxygen that's of course present in the air to form metal oxides. And we can see it happening when we see a formation of a dull layer on top of a metal. Well, this dull layer is actually that metal oxide. An example of this is when sodium reacts with oxygen to form sodium oxide. As we can see here, that metal has reacted and oxidized in the air to form sodium oxide, which would appear to be a dull layer on that metal. Now, not all metals will oxidize. It does depend on how reactive the metal is. For instance, gold, a very unreactive metal, won't oxidize. So this brings us to corrosion. What is corrosion? Well, corrosion is the process when a metal continues to oxidize and it becomes weaker over time. Now, an example of corrosion that we're very familiar with is the process of rusting. Now, this happens when iron or steel reacts with both oxygen and water. Now, this process of rusting can be represented using this equation. So iron plus oxygen plus water makes hydrated iron 3 oxide. It's important that we remember those little Roman numerals, don't miss those out. And that is what that orange-brown substance of rust actually is. That is its chemical name, hydrated iron 3 oxide. So we can investigate these factors that affect corrosion. If we have a look at these 3 different test tubes, we can see that test tube A has an iron nail just sitting in some water. We can see that test tube B has the same thing. It's got an iron nail sitting in boiled water. However, it's coated with a layer of oil. And in test tube C, we have an iron nail. It's not in water, but it is sitting in some calcium chloride. What we will observe over time is that only the nail in test tube A will rust. This is because in test tube A we have both air and water present. However, in test tube B, that oil removes the air. It stops the oxygen getting through to that nail. And in test tube C, we have the presence of that desiccant calcium chloride, which removes water. Now, this shows us that we need both of these to be present, not just one of them, for rusting to occur. Now, it's important that we think about how we can prevent rusting, because rust, of course, damages materials. So if we think about what we need for rust to take place, we need oxygen. Well, a great way to stop rusting happen then is to remove the oxygen. We could do this by using a barrier method such as painting, or we could store the metal in an unreactive gas such as nitrogen. Now, for rust to take place, we also need water. So another way that we could prevent rusting is by removing the water. Now again, we could use a barrier method such as painting that metal, or we could store the metal in a desiccant. This is a substance such as calcium chloride. Now, you might be wondering what this is, but I can assure you you've got some everyday experience of this. You might know when you open up a shoebox, for instance, you get that little white packet which says "do not eat." And that is the desiccant that is there to prevent moisture building up and potentially moulding happen. Probably isn't there to prevent rusting in that case, but it's the same substance. finally, we could use sacrificial protection, which is putting the metal in contact with a more reactive metal. Let's have a look now at each of these in a bit more detail. There are several different physical barrier methods that we can use. We can do painting, coating in oil, coating with plastic and electroplating. And this applies to the oxidation of all of the different metals, particularly focusing though on rusting of iron or steel. If we look at aluminium though, aluminium is quite a special metal because it reacts with oxygen and ends up forming a thin layer of aluminium oxide. Well, this acts as its own physical barrier and it protects it from corrosion. Sacrificial protection is a good alternative method of preventing rusting. The way it works is we put iron or steel in contact with a more reactive metal such as zinc, and this prevents rusting. The way that this works is the more reactive metal will oxidize instead of the iron. It sacrifices itself. And we can say that the iron is galvanized with zinc. The good thing about this is we can replace the more reactive metal, for instance that's zinc, as it corrodes, and that doesn't affect the iron. Most metals that we use in everyday use are actually alloys. We need to know a few specific examples for this exam. So we need to know that brass is made up of copper and zinc. We need to know that it's got some really important properties, such as the fact that it's resistant to corrosion and malleable. Now these properties make it really useful for lots of jobs, for instance pins in electrical plugs and musical instruments. Now bronze on the other hand, that is composed of copper and tin. Bronze is also resistant to corrosion, and we'll often see statues and coins made from bronze. Now gold for jewellery actually isn't just pure gold, well rarely it is anyway. 24 karat gold would be 100% gold, but anything lower than that, such as 18 karat gold, is actually a mixture, an alloy of gold, silver, copper and zinc in varying degrees. Now gold for jewellery is stronger than pure gold, and it's resistant to corrosion and it is shiny. All of these things make them great for using for jewellery. Now we use iron to make steel. However, we get different types of steel. We get high carbon steel, low carbon steel and stainless steel. Now these different steels are iron alloyed with different amounts of different elements. Let's have a look at high carbon steel. High carbon steel is composed of iron and 1 to 2% carbon. It has the properties that make it strong and brittle, which makes it really useful for cutting tools. Low carbon steel, on the other hand, as the name sort of suggests, is iron and less than 1% carbon. Now low carbon steel is easy to shape and it is soft. This makes it great for using to make car body parts. Now stainless steel is iron alloyed with chromium and nickel. It's hard and it resists corrosion, which makes it really useful for things such as cutlery. Now, we can also make aluminium alloys as well. And there's many different types of aluminium alloy. We don't need to know about any specific aluminium alloys. However, we do need to know that generally speaking, aluminium alloys are low density, and that makes them useful for certain purposes, such as making aircraft parts. We need to know about 2 types of ceramics, glass ceramics and clay ceramics. Clay ceramics are used to make bricks and pottery. These are made by shaping wet clay and then heating it in a furnace. This causes crystal to form and join together. Now clay ceramics are brittle, hard and resistant to corrosion. So now let's think about glass ceramics. The main type of glass used is soda-lime glass. However, sometimes borosilicate glass is used instead. They have different uses. These different uses come from the fact that borosilicate glass has a much higher melting point than soda-lime glass. That means that we might want to use borosilicate glass. For certain purposes, that means it's going to get hot. Examples of this include laboratory glassware and oven glassware, whereas soda-lime glass we're just going to use for everyday glass objects like the glasses that we drink out of. Now, soda lime glass we make using a mixture of sand, sodium carbonate and limestone heated together, and that gives us this brittle, transparent soda lime glass. Borosilicate glass, on the other hand, is made when we heat sand with boron trioxide. That's what gives us that characteristic high melting point. In this topic, we need to know the difference between low-density polyethylene and high-density polyethylene. Well, low-density polyethylene is formed when addition polymerization of ethene is carried out under high pressure and with a small amount of oxygen present. As a result of these special conditions, we make branched polymer chains. Now, these branched chains cannot pack together, and this gives us our low-density polyethylene. Now, on the other hand, we've got high-density polyethylene, and we make this when we do the addition polymerization of ethene, but under 50 degrees C with a catalyst present. Using this method, we make straight polymer chains, and these straight chains can pack together very closely, making it high density. We need to be able to compare the properties and uses of low-density polyethylene and high-density polyethylene. So low-density polyethylene, or LDPE, is flexible and unreactive. That makes it really useful for things such as plastic carrier bags. Now, high-density polyethylene, or HDPE, is strong, it's flexible, and it's resistant to shattering. That makes it really useful for making plastic pipes and bottles. We also need to know the difference between thermosoftening polymers and thermosetting polymers. We need to know that thermosoftening polymers do not have crosslinks between the different polymer chains, and as a result, they will melt when they are heated. Thermosetting polymers, on the other hand, have strong covalent crosslinks between the polymer chains, and because of these strong covalent crosslinks, they do not melt when they're heated. Composites are made of two materials, a main material called a matrix, and fibres or fragments of other materials that we add to this matrix. We call these materials reinforcements. Everyday examples of composites include plywood and concrete. We need to know about the Haber process. In the Haber process, nitrogen and hydrogen gases get pumped into the system. Now, in this system, we're going to ramp up the pressure to 200 atmospheres. The temperature is going to get increased to 450 degrees C. And these gases of nitrogen and hydrogen are going to be passed over an ion catalyst. Now, the reaction mixture is going to get cooled. The reason for this is that as ammonia gets formed, it will be a gas. To remove it, we want to condense it back down to a liquid so that we can open up a tap and drain it away. So, now that we've done that and we've removed the ammonia that we've made, we're going to recycle any leftover nitrogen and hydrogen. To summarise the Haber process, we need to make sure that we know these key facts. So nitrogen plus hydrogen makes ammonia. And the balanced chemical equation for this is N2 gaseous plus 3H2 gaseous goes to make, with a reversible arrow, 2NH3 gaseous. We need to make sure that we know these three conditions for the Haber process. We need to know that we need an ion catalyst, 450 degrees C temperature, and 200 atmosphere pressure. We also need to know where we're getting the raw materials of nitrogen and hydrogen from. Nitrogen is coming from the air, and hydrogen is coming from natural gas. Now, in industry, we have to think of a lot of factors when deciding what conditions to use. We need to think about the cost of energy and the availability of raw materials. We need to have a think about the conditions that are needed to get that right balance between getting a good yield, also having a good rate of reaction. Now, this is really important because it might seem obvious that we want to get the highest yield. However, we don't want to get that highest yield if it's going to be so slow it takes thousands of years to get that maximum yield. We need to weigh this up. So, looking at the Haber process and using what we've just said, we know to get a maximum yield of ammonia, we need low temperatures so that it shifts in that forward exothermic direction, and high pressures so it shifts to that side with the fewer moles. However, if we break these down, we know that low temperatures will actually slow down the rate of that reaction a lot. So we need to compromise and use a temperature somewhere in the middle. So we use 450 degrees C so that we have a fast enough reaction and enough yield. Now we know that high pressures is good for the Haber process. Now that works out well because we know higher pressures increases the rate of reaction. However, high pressures can be quite dangerous. So we're going to slightly lower the pressure to 200 atmospheres. We also add an iron catalyst during the Haber process, and that's because this will increase the rate of reaction. Some of the substances needed to make fertilisers get mined from the earth. So potassium chloride is one of these substances. This can be used as a fertiliser straight away after mining because it contains these soluble potassium ions. Now potassium sulfate is also something that can be used as a fertiliser immediately after mining. And this is again because it contains those soluble potassium ions. Then finally we have potassium rock. Now this is insoluble. Therefore, we can't use it as a fertiliser immediately after mining it. We need to process it so that we can use it as a fertiliser. Now, there's 3 reactions that this phosphate rock can go through to make it into something that can be used as a fertiliser. And we need to know these 3 reactions. So the first reaction is the phosphate rock can be reacted with nitric acid. So when this happens, we end up making calcium nitrate and phosphoric acid. The phosphoric acid can then be neutralised by ammonia to make ammonium phosphate. This can be used as a fertiliser. Then we can take the phosphate rock and we can react it with sulfuric acid. This makes a single superphosphate, which is actually calcium phosphate and calcium sulfate. Finally, that phosphate rock, we can react it with phosphoric acid. By doing this, we make triple superphosphate, which is simply just calcium phosphate. So those are our 3 reactions that we can put the phosphate rock through to make something that we can use as a fertiliser. We need to be able to compare the industrial and laboratory methods of producing fertilisers. This table below summarises everything we need to know about these processes and how we can compare them. So the industrial production of NPK fertilisers is a continuous process. We're continually making these fertilisers. If we compare this to the laboratory methods, this is just a batch process. We might decide that today we want to make a certain type of fertiliser, so we set it up to make a batch of that. Next up, industrial processes is a very large scale production. We're trying to make this on enormous scales, whereas in the lab, maybe we're just making it for ourselves in a small scale production. Industrially, the production of these NPK fertilisers is an automatic process. So that means that the machinery and computers will be used to minimise the labour and running costs. Everything happens on a little process that is automated. However, in the lab, it's very labour intensive. There's going to be someone there doing every step of the way, and therefore it has high running costs. Industrial processes have a very fast production speed due to all these automations, whereas in the lab it's very slow. Finally, industrially, reactants get made from the raw materials. Because this has been done on such a large scale, we can make everything from the raw materials, which in the end makes it much more cost effective. However, in the lab, we don't do this. We instead purchase the reactants from a supplier. So that's our general comparison, and this is true throughout chemistry of things made industrially versus in the lab. And in an everyday example, we can imagine this like you're at the McVitie's factory making biscuits on an enormous scale, making millions and millions of biscuits a day, versus in a little home bakery where we're just making some little cookies and cakes to order. It's a completely different process, and you can appreciate differences in the speed, the automation, and so on. Hopefully that will help you relate this to real life. Now, ammonium sulfate is another salt that can be used as a fertiliser. We can make this in the lab using the following reaction. So ammonia plus sulfuric acid makes ammonium sulfate. Now, in this case, because both the ammonia and the sulfuric acid are soluble, in order to make ammonium sulfate, we must carry out a titration. Now, this process in the lab is a batch process, which means that we're just making small amounts of ammonium sulfate at a time, and after each process, we'll have to clean out all of our apparatus and start again. We need to be able to describe an experiment to make this ammonium sulfate in the lab. So the first step we're going to take is we're going to put some dilute sulfuric acid into a conical flask. We're then going to add a few drops of methyl orange indicator. We'll then add some dilute ammonia drop by drop using a burette and stir between each drop. We're going to continue adding ammonia until eventually we get a colour change from red to yellow. We're going to add a few more drops of dilute ammonia solution. This is to make sure that this has fully reacted, and we're not going to worry about there being an excess of ammonia because it will just evaporate off. We're then going to pour the mixture into an evaporating basin, and then we're going to heat it using a water bath. The reason for doing this is to start the evaporation of some of this water that's in the solution, and of course to remove any of that excess ammonia. Now, before all the water evaporates, we're going to remove this from the heat, and we're going to leave it until crystals begin to form. At that point, we're going to pour away any excess water, and then we're going to leave it to crystallise in a warm oven. Now, we also make ammonium sulfate in industry as well, on a very, very large scale. Now, when making ammonium sulfate in industry, the reactants of ammonia and sulfuric acid are actually made from their raw materials. Industry uses a continuous process, which means that we're never shutting off the machine. We're continually making this ammonium sulfate and continually putting in new reactants to then be able to make even more. So this flowchart here shows how we make this. We can see we're making the nitrogen from the raw material of air. Hydrogen you can see we get from the raw materials of natural gas and water. And the nitrogen and the hydrogen we use to make that ammonia that's needed to make the ammonium sulfate. Now the sulfuric acid, on the other hand, that we need, we make via making sulfur trioxide. So we use sulfur and air to make our sulfur trioxide, and then react that with some more water to make our sulfuric acid. Once we've got that ammonia and sulfuric acid, we finish off by making our ammonium sulfate.
Ouch! This is why in some videos I explain scratches.